the assumptions that I made. I write here, first assumption, stationarity. Second assumption, Gaussianity. There is the assumption of linearity. This is usually not mentioned because it's already evident from the relationship that you have written, so it's redundant to say I'm assuming linearity. Because if you look at the relationship, of course, you are assuming linearity, so usually it's not indicated. 3, independence of epsilon stationarity, let's say also ergodicity. To be more clear. Then there is a fourth one, which is the mean value of epsilon should be 0. And also the mean value of x should be 0. So the mean values of the two variables, x and epsilon, should be 0. And don't be concerned, because it's very easy to bring a time series to the 0 mean condition. It's just enough to subtract from any value of the time series the mean value. So if you have a time series that has a mean of 10, if you subtract from any observation the value of 10, you get a 0 mean time series. So don't be concerned by these assumptions, but still you may ask me why they are needed. And indeed, I think it's worth explaining why they are needed. First of all, these assumptions, the 0 mean for x and epsilon, are stated in this way, which is not really very rigorous. The assumption should be that they have the same average value. This is the formal and rigorous assumption. Epsilon and x should have the same average. And the fact that we impose that both should have 0 mean is just for simplicity in writing. Because otherwise the relationship would become more complicated. So now let me explain to you, which is very easy, why they should have the same mean. Okay? Let's look at this relationship here. And let's take the average at the left-hand side and right-hand side. So let's take the expected value, which means computing the average in practice of xt. And this is equal to the expected value at the right-hand side, which means expected value just 1 second, the formalism is the expected value of, I can take phi1 out of the expectation, x plus the expected value of epsilon t. which is expectation. So now let's suppose that, first of all, let's note that the expected value of xt and the expected value of xt minus 1 are the same quantity because of the assumption of stationarity. So now let's assume that both x and epsilon have zero mean. Let's assume that they have zero mean, which means that expectation of xt is 0, expectation of xt minus 1 is 0, expectation of epsilon is 0, the assumption is satisfied. This relationship satisfies the assumption that both should have zero mean. Instead, if you assume that the expected value of epsilon is different from 0, this relationship will be satisfied. This means that if you assume that you have a linear relationship like this one, the linear relationship expressed by an autoregressive model, to make it working, you have to work with zero mean variables. As I said, but I don't want to go into details, it can be proved that the rigid condition is that they have the same mean. And we could write in a different way this linear relationship for the case in which their mean is not 0. It's equal but not 0. We could write this linear relationship in a different way, and we could get the relationship below, which would be different as well, satisfied. I don't want to give details on this because I don't want to insist too much on the mathematics. It's not really relevant. What I just want you to know is that the strict condition is that they have the same mean. And let's assume that this same mean is 0, because it's easier to write. So basically I got, as you see, 4 assumptions. These are the assumptions that condition the veridicity, the reliability of this stochastic representation. Good. Let's keep into account that independence of epsilon means that the variable epsilon is completely unpredictable. It's random. It's the random component of the stochastic process. Okay. Now, in statistics, one good thing is that you are provided means for checking the assumptions. Not all of them, but in many cases, statistics provides you with tests to check if the assumptions are satisfied. So let's have a look at what are these tests in this case. And keep into account that in statistics, when you perform a test, the test doesn't tell you for sure that the assumption is satisfied. The test gives to you a probability that the assumption is satisfied, like the confidence bands, which I will come back soon to check the independence of epsilon. So the test tells you, look, at the 95% of probability your assumption is satisfied. And another thing that I want you just to record in your mind, this is never the case. Statistics doesn't tell you that an assumption is satisfied. And I tell you this because, you know, if you go and you look for more information, you go on the web, on Wikipedia, and look for something related to statistical tests, you would find a different wording with respect to what I'm telling you. Because statistics doesn't tell you that an assumption is satisfied. Statistics does tell you that you cannot reject the fact that the assumption is not satisfied. So it doesn't tell you yes, it tells you not. Okay? Because, you know, this is an important difference. Because one thing is to tell one person, look, if you take this way, you are right, with 95% probability. Another thing is to tell this person, if you don't take this way, you are not wrong, with 95% probability. It's different. And if you think to yourself, if you are told a similar thing, one thing is if you are told you are right 95%. One thing is if you are told you are not wrong at the 95%. It's a bit different. The meaning is different. And also the practical understanding is different. So statistics doesn't tell you never certainties. It tells you always probabilities, and therefore the correct terminology, probability that you are not wrong, not a probability that you are right. Okay? Telling you a probability that you are right is something more, because if one tells you you are not wrong, it means that indeed you are right, but there could be different ways of being right. So it's a bit different, but this is almost philosophical. So let's forget about this, and let's, for our purposes, to assume that a test tells you 95% probability to be right. Okay? I just wanted you to know that if you take more information, this is not the wording that you will find. So, how can we test this? First of all, stationarity and ergodicity. This is a bit of a problem, because statistics doesn't tell us any test to assume stationarity and ergodicity. So there is no way for us to look at a time series and to make assumptions of stationarity on the underlying process. This is not possible. Of course, what you can do is look at the time series for the case of the Po River and look if there are changes. Just look at it. And are there any changes? Do you see evident changes? If you see them, okay, of course you know that the assumption of stationarity is wrong. If you don't see them, you can move forward. But there is no formal test. And also keep in mind that we are talking about statistics, but we are also talking about real processes. So think of the real process. Do you think that the river flow of the Po River can be assumed to be stationary, or do you see any relevant change? Like a dam was built, and on the Po River many dams were built in the past 100 years, but one may say their capacity overall is quite limited, so their influence on the river flows is not so strong. So think at the process, look at the realization of the process, and then this is the way in which we usually test stationarity and ergodicity. And there is a long debate now also in engineering, because people say that when you talk of natural processes, stationarity is, strictly speaking, never satisfied. And I agree. Strictly speaking, is never satisfied. But look, we are engineers. We are not looking for an explanation that is physically correct. We look for assumption that allows us to make design. This is a huge difference. Even if I'm sure that stationarity is not satisfied, I can assume stationarity if I am convinced that this assumption gives to me the capability to provide a good design. So basically, I know that the river flows for sure are changing. If you look at the long period, we had glaciations, and so for sure the river flows changed. But if I have to design a dam and I look into the future for 100 years, and I ask myself if the past 100 years can give me an indication of the shape of the future, I would say for designing a dam, for sure yes. Because if I don't believe in a rapid climate change, I say this is fine. Climate will for sure change in 1,000 years. But if I don't believe in the rapid climate change, I can assume stationarity. So let's also think at assumptions in a very practical way. We don't have to ask ourselves as engineers if they are really satisfied. We have to ask ourselves if they are reliable for designing. Okay. Second test, Gaussianity. Gaussianity, it's easy to check because you draw the probability density of a realization and you look at it. And there are also formal tests, which I'm not explaining to you, that tell you if the assumption of Gaussianity is reliable. If you look at the probability density, you know that the Gaussian density is symmetric around the mean. So if you look at the tails of the probability density and the shape around the mean, you can get an indication of if it is satisfied. There are also formal tests. Okay? So I'm not spending more time. Independence. First test that you have to make, independence of epsilon, is to draw the autocorrelation function. Are the autocorrelation coefficients included in the famous band of the zero value or not? If they are, this is a first test that tells you that the variable is independent. But keep in mind this is a necessary condition, not sufficient. The fact that you find an autocorrelation function for epsilon which is included into the blue band, with the exception of the first, of course, lag 0 is always out. But if you find all the coefficients that are included in the blue band, this is a necessary condition, it's not sufficient. So let me tell you some more. What is then another condition that we should check if it is satisfied to make sure that epsilon is independent. And this is a very important thing that you have to remember. I tell you another condition, which is another necessary condition. And the combination of the two, autocorrelation function of epsilon plus this second necessary condition that I'm telling you, the combination of the two is, let's say, almost a sufficient condition. Not really always, but almost a sufficient condition. So, what is the second condition? And I write here again xt equal phi 1 xt minus 1 plus epsilon t. I said that epsilon should be unpredictable and therefore should have no autocorrelation. Okay. Another thing is that it shouldn't be predictable by looking at past x. So epsilon should be independent, have no memory with respect to itself, but also should have no memory with respect to past x. Because if by looking at past x I can predict epsilon in the future, then it means that it's predictable, not unpredictable. So basically, it's not just enough to check that it doesn't depend on itself. I have to check that it doesn't depend on past x. Because of course, if you look at x and epsilon at the same time, they are dependent. They are related by a linear relationship, so they are dependent. But epsilon should be independent by past x. So there is another coefficient called cross-correlation coefficient that allows you to look at the correlation among the different variables. And let me just show you, it is often indicated as rho x epsilon at like L, which is 1 over n summation from at the denominator we have sigma x, sigma epsilon. For the correlation coefficient, you may remember we had sigma square of x. In this case, we have the product of the sigmas. And at the numerator, we have summation from a equal 1 to n minus L of let me see, x I. One could put here t, it's better, t equal 1 to n minus L, like in my definition of the autocorrelation coefficient, x t epsilon t plus L. Remember that the mean is 0. The mean of x and epsilon is 0. Because in the definition that I gave of the autocorrelation coefficient, it was a bit, there was the difference between the variable and the mean. In this case, the mean is 0. So you see that here we have the product between xt and epsilon, future epsilon. And these are the two variables that should be independent. So basically, there are two things to note here. First of all, L can be positive or negative, because we can study the correlation between x and future epsilon or past epsilon. Past epsilon. So we can study the correlation between x and future or past epsilon. So L can be positive or negative. And what is important for us, accordingly to this formulation, is that for positive L's, we get rho L equal to 0. Rho L x epsilon equal to 0. And the way in which, this is a question that I usually ask at the exam, the way you have to state it is that epsilon should be independent of past x. There is one, let me see. Yeah, of course the mean 0, this is very easy to check. So, let me try to summarize what I did so far. I introduced a linear relationship to keep memory into account, and this linear relationship is composed by a deterministic part plus a random part. The random part is independent. So what I did is to transform the data, to introduce a relationship to explain the data, and this relationship is composed by a deterministic part, which takes memory into account, plus a random part. And now, I can treat the random part as an independent variable, so a probability distribution suffices. And the deterministic part allows me to reproduce the memory. And I introduced the assumptions that this kind of representation needs, and also we spoke about how to check if they are satisfied. And there is one final thing that I want to tell you before I explain how to generate data, because once that we accept this representation to generate data is very easy. And one final thing, stationarity. I said that it cannot be checked, but I can say what are the mathematical conditions on this process to make sure that it's stationary. And stationarity for a AR1 process imply that the absolute value of phi1 is less than 1. And please note that if you downloaded already these slides, there is an equal sign also. And this was a mistake that I corrected in the new version that I put on my website. So the absolute value shouldn't be less or equal than 1, should be less than 1. And this is easy to understand because if you look at the formula here, you would notice that if phi1 is greater than 1, is 2, for instance, then the process would grow continuously up. Because, you know, if you start from like from here, this is xt, this is t, then if you assume that phi1 is 2, then the next point would be twice the previous one, plus something that has a mean of 0. So it could be, even if the something, the plus something is negative, it will be sometimes negative, sometimes positive. But even if it's negative, and then you go back to this, then at the next step, you have again an increase, plus something which has mean 0, which may be positive this time, and you go here, and then here, and then here. So you would have a continuous increase. Why this is a zero mean variable, so it can be continuously increasing. Instead, if you take this one lower than 1, you see that you have always a decrease. And always a decrease means that you converge to the mean, which is 0, which is fine. Okay, so assumptions are here. Here there is no stationarity, and because, you know, it's not listed here because it's not verifiable. So in the slides I didn't write stationarity, but apart from stationarity they are the same. Now let me show you how we can generate with this process. And let's assume that we know what is phi1. Phi1 we said that should be lower than 1. Let's suppose that it's 0.5. So how we can generate a series for this process? The first thing that we have to do is to generate a series for epsilon. And this is easy to do. We know how to do it because epsilon has no memory. And we know that it's Gaussian. So we can just generate epsilon by using the R norm function, which we already know. And to do so, we need to know how many items we want to generate, and I put 1000. We need to know the mean, 0, because by assumption it's 0. And we need to know the standard deviation. The standard deviation is something that indeed we need to identify on the data. It's a parameter of this model. You know what parameters are. So the standard deviation, let's make an assumption. Let's assume that it's 0.5. But let's also notice that we don't know so far how to estimate it. Okay? So this is our generation. And we can look at the autocorrelation function and see what happens. You see the autocorrelation function. All the coefficients are within the blue bands. not really all, because you see there is one that is out, 1 in 30. Fine, because I said we can tolerate 5 over 100. So 1 in 30 is fine. Okay, good. Now let me simulate x. It's very easy. At each time step, we have to multiply xt minus 1 by phi 1 and add epsilon t. We have a problem here. When we start the simulation at time 1, we don't have the x at t minus 1, x0. We don't have it. We need a boundary condition. An initial condition, sorry. We need an initial condition for x. And given that x has a zero mean, let's assume that x one is equal to 0. I should have written x equal vector and then x1 equals 0. I put x1 because R doesn't accept the 0 as index for a vector, so I have to start from 1. Now I can write a fourth cycle for I in 2 to 1000 and then I can write x I equal to, I said 0.5 for phi 1, 0.5 times x I minus 1 plus PR I. It was PR1, sorry. So let me do like this. Done. Done. Now, let's look, because I didn't do that so far, let's plot PR1 epsilon. I forgot. I don't understand why I need to do this, but let me use a line. This is epsilon. Look at the variability between minus 1.5 to plus 1.5. And now let me plot. I don't remember how to start. Okay. So look at this graph, and now let's plot x. So what's the difference here? First of all, look at the variability, which is higher. It's increased, and it became 2. And look at, you see the series that is less, before it was more compact. Now it seems that there are some patterns. Let's look at the autocorrelation now. ACF X. You see that there is some positive correlation, which vanishes after about lag 3. So it's not really, it doesn't look similar to the series of the Paul River, but there is indeed correlation. Now, let me do this. let me redo the generation by using not 0.5 but 0.9 as correlation coefficient. So what is your guess? If you look at the plot of the time series, would you expect an increased variability or a decreased variability? It was between -2 and 2 before. Yeah, I forgot, sorry. So what is your guess? More variability with an autocorrelation coefficient, with, autoregressive coefficient increased, or lower variability? Just think to it, and then don't give to me the reply. Just think to it. More variability. So if we increase the memory, if we increase the relationship between each variable and the previous one, we get more variability. And also what you see is that now you see the patterns, the cycles. Do you remember the comparison that I plot you with the series of epsilon? You see here is more compacted. And now let's look at the autocorrelation function. Even in this case, make your guess. Make your guess. And here it is. You see that now the memory is stronger and lasts for about 15 lags. This is more similar to the series of the Poor River. It's indeed not really similar, because you know, if I plotted this autocorrelation function for a